Picture the night sky, the vast darkness sprinkled with stars, most of them solitary or paired, twinkling like distant lighthouses. Now imagine not 2, not 4, but 8 stars locked in an intricate cosmic dance, bound together by gravity in a single system. This isn't science fiction, it's the baffling reality of octuple star systems, some of the rarest and most mysterious structures in our universe. These stellar families defy expectations, spinning and orbiting in patterns so complex they challenge everything we thought we knew about how stars form and interact. And today, we're diving deep into 30 of the strangest discoveries scientists have uncovered about them, each one more mind-bending than the last. What makes an octuple star system so extraordinary? Think of it like a celestial ballet with 8 performers, each pulling the others in different directions, yet somehow maintaining a precarious balance. Most star systems are simple single stars like our Sun, or binaries where 2 stars orbit each other, but 8, that's chaos wrapped in gravity's embrace. These systems shouldn't exist according to early astronomical models, yet here they are, whispering secrets about the violent, crowded nurseries where stars are born. Some of them host planets caught in a dizzying tug of war between multiple suns, where a single day might see sunrises and sunsets in rapid, unpredictable succession. The discoveries surrounding these systems are as strange as they are groundbreaking. From stars orbiting each other at breakneck speeds to unexplained gaps in their formation histories, octuple star systems are rewriting the rules of astrophysics. Why do some of these systems have stars that seem far too young to coexist with their ancient siblings? How do their planets, if they have any, survive the gravitational chaos? And what can these cosmic oddities teach us about the origins of our own solar system? Strap in, because the answers are more bizarre than anything we could have imagined. By the end of this journey, you'll see the night sky and the universe itself in a whole new light. The first confirmed octuple star system, known as STRS0509-0520, stunned astronomers when it was discovered in 2015. Nestled within the massive star-forming region called the Trapezium Cluster in the heart of the Orion Nebula, this system shattered long-held assumptions about how many stars could remain gravitationally bound. Before this discovery, scientists believed complex groupings beyond 6 stars were too unstable to survive. The gravitational forces would inevitably tear them apart or fling stars into the void. Yet here was a cosmic family of 8, some so close they orbit each other in mere days while others swing wide in slower, looping paths. The team behind the breakthrough, led by astronomer Kevin Luhman, used the powerful Hubble Space Telescope alongside infrared data to untangle this stellar knot. What they found was a hierarchical system, smaller groups of stars orbiting each other in tight pairs or trios, which themselves circle a common center. It's like a celestial version of Russian nesting dolls, where each layer of motion influences the next. One pair in this system whips around so fast their combined glow pulses like a lighthouse beacon, while another duo is separated by a distance comparable to Neptune's orbit around our Sun. What made this discovery so revolutionary wasn't just the number of stars, it was their survival. Young star systems are violent places where gravitational shoving matches often eject weaker siblings. The fact that 8 stars remained tied together suggested a far more gentle birth than theorists predicted, possibly forming from a single, unusually massive cloud of gas that fragmented in just the right way. Even more puzzling, the stars varied wildly in age, hinting at multiple episodes of star formation within the same system. This wasn't just a challenge to astrophysics, it was a cosmic puzzle box, forcing scientists to rethink how stellar families evolve in the universe's busiest neighborhoods. The implications ripple far beyond Orion. If octuple systems can form in dense clusters where gravitational chaos reigns, could even larger groupings exist undetected? And what does it mean for planets trying to form in such turbulent environments? Suddenly, the universe's stellar rulebook had missing pages, and astronomers were eager to read them. Gravity is the unseen choreographer in octuple star systems, but its dance moves are anything but orderly. With 8 massive bodies pulling on one another, the resulting gravitational tug-of-war creates orbits that look more like tangled spaghetti than the neat circles we're used to in simpler systems. Imagine 8 children holding hands and spinning wildly on a playground, some faster, some slower, some yanking harder than others. Now replace those children with stars, each weighing hundreds of thousands of times more than Earth, and you've got a glimpse of the chaos unfolding in these cosmic arenas. One of the most startling findings is how often stars in these systems get flung into space like cosmic outcasts. Computer simulations show that even a slight nudge from a nearby star can destabilize delicate orbital balances, sending one or more stars careening into the void at speeds exceeding 100,000 miles per hour. Astronomers call this gravitational slingshotting, and it's not just theoretical observations of runaway stars streaking through galaxies with unusual trajectories. Often trace their origins back to violent ejections from overcrowded systems like these. But the real head-scratcher, some stars in octuple systems somehow avoid this fate, settling into orbits so precise they defy the odds. Take the system HD 96064, where 4 pairs of stars orbit each other in near-perfect sync, almost as if they're locked in an endless game of gravitational leapfrog. The secret lies in their spacing, just far enough apart to avoid catastrophic collisions, yet close enough to keep their dance intact for millions of years. It's a cosmic tightrope walk where one misstep could unravel the entire arrangement, yet even these stable systems hold surprises. In 2022, radio telescopes caught a bizarre signal from the octuple system Cassiopeia, a rhythmic pulsing that revealed 2 stars pirouetting around each other every 3.5 days, while a third star circled them both in a lopsided egg-shaped orbit. This kind of asymmetry shouldn't last long according to classical physics, yet there it was, stubbornly persisting. Theorists now suspect hidden forces at play, like magnetic fields or swirling disks of leftover star-forming gas, acting as invisible hands that tweak the rules of gravity's game. The implications ripple beyond celestial mechanics. If stars can be ejected so easily from these systems, what happens to their planets? Any world orbiting a star that gets kicked out would face a nightmare scenario, either torn apart by tidal forces or left drifting in permanent deep freeze. Meanwhile, planets that stay behind would endure wild temperature swings as their multiple suns rise and set in erratic patterns. It's a reminder that in the universe's most crowded neighborhoods, survival hinges on a fragile balance, and octuple star systems are the ultimate test of gravity's patience. If you think navigating rush-hour traffic is chaotic, spare a thought for any planet trying to survive in an octuple star system. The gravitational maelstrom created by 8 stars means planetary orbits in these systems are anything but stable. They're cosmic roller coasters with no safety harness. While most planets in our galaxy enjoy predictable, elliptical paths around a single star, worlds in these extreme environments face relentless tug-of-war battles between multiple gravitational masters. One miscalculation, one slight shift in balance, and a planet could be sent careening into deep space or smashed to pieces in a catastrophic collision. Take the hypothetical planet circling the octuple system Nu Orionis, assuming it could form at all amidst the stellar chaos. Simulations show its orbit would resemble a tangled knot more than a smooth ellipse, zigzagging unpredictably as competing stars yank it in different directions. Some days it might bask in the warmth of 4 suns simultaneously, only to be plunged into freezing darkness the next as its path carries it beyond their reach. The gravitational stresses alone would stretch its crust, triggering apocalyptic volcanic eruptions and earthquakes. Worst-case scenario, a close encounter with a passing star could fling it outward like a slingshot, doomed to wander the galaxy as a rogue planet, untethered from any solar warmth. Real-world observations back up these terrifying models. In 2021, astronomers spotted a Jupiter-sized exoplanet in the quadruple star system 34 light-years away, its orbit so erratic they dubbed it the pinball planet. Extrapolate that instability to an octuple system, and the stakes multiply exponentially. Some theorists argue planets here might not even have traditional orbits instead. They could be transient captives, temporarily bound to one star before being snatched away by another, like a cosmic game of hot potato. Yet against all odds, a handful of worlds might cling to survival in what scientists call sweet spots, regions where gravitational forces between stars briefly cancel each other out. It's like finding the eye of a hurricane, a precarious zone of calm where a planet could theoretically maintain a stable orbit for millennia. The catch: these zones are vanishingly rare and often short-lived. A passing star's nudge or the slow drift of orbits over time can erase them in astronomical blink, sending any hopeful worlds back into the chaos. What does this mean for the possibility of life? In these frenzied systems, planets face constant bombardment from shifting radiation belts and erratic temperature swings, conditions that would strip away atmospheres and boil off oceans. Any life forms hardy enough to endure would need to evolve under the ultimate survival pressure, adapting to a world where the very concept of a year could change overnight. It's a stark reminder that while octuple star systems push the boundaries of cosmic architecture, they're also nature's ultimate laboratories for destruction and reinvention. If you thought mood lighting was unpredictable, try observing an octuple star system where the combined glow of 8 suns creates a flickering spectacle that's left astronomers scratching their heads. These systems don't just twinkle like solitary stars, they unleash chaotic light shows, their brightness surging and plummeting in ways that defy conventional models. One moment, the system might shine with the intensity of a dozen suns as multiple stars align. The next, it could dim to near invisibility when stellar orbits cast overlapping shadows, like cosmic lamp switches being flipped at random. Take the system V358 Orionis, where telescopes recorded a staggering 30-fold increase in brightness over just 48 hours, an unprecedented swing that sent researchers scrambling for explanations. At first, they suspected a superflare or colliding stars, but the answer was far stranger. 4 of the system's stars had synced up in a temporary alignment, their light combining like overlapping spotlights on a stage. Meanwhile, another pair eclipsed each other precisely as a third star passed behind interstellar dust, creating a perfect storm of optical illusions. Untangling this required painstakingly separating each star's contribution from the light soup, a feat akin to identifying individual instruments in a symphony played at double speed. The challenges don't stop there. Some octuple systems exhibit heartbeat variations, rhythmic pulses caused by tides of plasma stretching between stars as they orbit perilously close. In system MT91305, one star's gravity distorts its companion into an egg shape every orbit, squeezing it like a stress ball until it rebounds, releasing bursts of light detectable across interstellar space. Other systems flicker erratically due to starspots, massive magnetic storms larger than our sun's diameter rotating in and out of view across multiple stellar surfaces simultaneously. But the real head-scratchers are the systems where light patterns repeat in cycles too precise for random chance, yet too complex for current physics to explain. In 2019, the octuple system TYC 7037096 baffled scientists with a 17-day brightness cycle that appeared coordinated across 3 separate star pairs, as if orchestrated by an unseen conductor. Some theorize gravitational resonances, subtle tugs that sync orbits across vast distances, might be at play, while others speculate we're witnessing the aftermath of a stellar breakup, where leftover debris clouds twist the light like a cosmic funhouse mirror. For astronomers, these light variations aren't just celestial quirks, they're vital clues. Each flicker encodes information about stellar masses, distances, and even hidden companions. But decoding them means inventing new analytical tools on the fly, pushing signal processing algorithms to their limits. It's a reminder that in the universe's most crowded neighborhoods, even light can't travel straight forwardly. It becomes a prisoner of gravity's labyrinth, bending and twisting in ways we're only beginning to understand. Among the countless oddities of octuple star systems, few are as visually breathtaking or scientifically revealing as their rare stellar alignments. Imagine standing on a hypothetical planet within one of these systems and looking up to see not one, not two, but several suns crisscrossing the sky in an elaborate celestial waltz. There might be moments when 3 stars line up perfectly, casting overlapping shadows, or brief instants when 4 suns dip below the horizon in unison, plunging the landscape into sudden twilight. These aren't just hypothetical scenarios. Real observations confirm that in systems like V906 Scorpii, such alignments create light patterns so precise they could double as cosmic clocks. One particularly mesmerizing phenomenon occurs when multiple stars eclipse each other simultaneously. In binary systems, eclipses happen predictably like clockwork, but add 6 more stars to the mix, and the timing becomes a chaotic masterpiece. The octuple system BRT000118 offers a jaw-dropping example. Infrared telescopes caught 2 separate eclipses happening at once, with one pair of stars sliding in front of each other while another duo did the same at a right angle. The result, a fleeting diamond-shaped shadow, a geometric wonder that lasted mere hours before the stars continued their endless chase. Even more mystifying are the ghost eclipses, events where star alignments produce theoretical shadows that should be visible from Earth, yet leave no trace in the light data. In system HD 123905A, 3 stars aligned perfectly in 2019. Calculations showed their combined shadows should have dimmed the system's brightness by 15%. Instead, the light dipped by only 2%, as if something invisible, perhaps a disk of debris or a warped gravitational lens, interfered. Theorists are still debating whether these phantom eclipses hint at undiscovered planets, interstellar dust clouds, or flaws in our understanding of how light bends around multiple massive objects. Then there are the stellar echoes, a phenomenon unique to systems with tight orbital dances. When stars in a compact group like a Cassiopeia pass behind one another, their light doesn't just vanish, it rebounds off nearby circumstellar material, creating delayed pulses of brightness that arrive days or even weeks later. It's akin to shouting into a canyon and hearing your voice bounce back from multiple walls, except here, the canyon is light years wide, and the echoes carry secrets about the system's hidden structure. For astronomers, these alignments aren't just cosmic eye candy. They're golden opportunities to measure stellar properties with uncanny precision. During a multi-star eclipse, subtle changes in light reveal atmospheric details of stars that would otherwise remain shrouded in glare. In system MTS-0509, a chance alignment exposed the faint signature of helium in a star's outer layers, something impossible to detect without another star backlighting it like a celestial spotlight. Other alignments have unveiled rogue gas strands stretching between stars, remnants of the messy birth that brought this stellar family together. Yet for all their beauty, these events underscore a deeper mystery. How do octuple systems maintain such intricate choreography over millions of years? In most cases, chaotic gravitational interactions should scramble orbits beyond recognition. Yet systems like STRS-0509 keep producing alignments as regular and as fragile as a house of cards in a breeze. Some researchers speculate magnetic fields act as invisible guides, while others propose these systems are younger than we think, their dances not yet disrupted by time. One thing's certain, every aligned eclipse, every ghostly shadow, whispers tantalizing hints about the forces holding these stellar families together or pulling them apart. In the cosmic melting pot of an octuple star system, stellar diversity reaches levels that shouldn't logically exist. Picture a family reunion where toddlers, teenagers, and centenarians all share the same backyard, except here, the family members are stars in radically different life stages, defying the usual rules of stellar neighborhoods. Most star clusters follow a predictable pattern, with stars of similar age and composition burning at comparable rates. But octuple systems, they're the ultimate outliers, hosting bizarre stellar retirement homes where newborn stars blaze alongside dying embers, all gravitationally shackled together in a cosmic paradox. Take the system ESO 55701, where astronomers found a blazing blue main sequence star, a youthful powerhouse burning at over 30,000 degrees, orbiting a lethargic red giant that's already in its death throes. These stars shouldn't coexist peacefully. The red giant's expansive outer layers should have engulfed its smaller neighbor long ago. Yet somehow they've maintained a delicate truce, separated by a distance barely wider than Saturn's orbit around our Sun. The secret lies in their speed. They whip around each other so fast that the red giant's slow-motion death can't keep up, like a tortoise trying to catch a hummingbird. Even stranger are systems like BT Monocerotes, where a dense white dwarf, the Earth-sized corpse of a dead star, circles a pair of lively yellow dwarfs still in their prime. White dwarfs typically form after billions of years, yet here one sits, its faint glow outshone by younger siblings. How did this happen? One theory suggests a violent stellar coup. The white dwarf might have been part of a different system originally, captured during a close encounter that booted out another star to maintain gravitational balance. It's a celestial game of musical chairs where losers get ejected into the void while winners cling to unstable orbits. Then there's the case of V404 Cygni, a system boasting not one but two Wolf-Rayet stars, rare, ultra-hot giants spewing out galactic winds at millions of miles per hour alongside a serene orange dwarf. Wolf-Rayet stars are notorious for their short, explosive lifespans, often detonating as supernova within a few million years. Finding them paired with a cooler, long-lived star is like discovering a volcano erupting next to a glacier. The only explanation: they likely formed from the same gas cloud but evolved at wildly different rates, with the Wolf-Rayet stars burning through their fuel at breakneck speed while their sibling hoarded its reserves. These mismatched stellar pairs force astronomers to rewrite the rules of stellar evolution. Normally, stars in a system share similar chemical compositions, having been born from the same parent cloud. But spectrographs reveal shocking disparities in octuple systems, some stars dripping with heavy metals forged in supernova, others pristine with primordial hydrogen, suggesting they were adopted from different cosmic neighborhoods. It's as if the universe tossed a handful of random stars into a gravitational blender, hitting puree and seeing what stuck. The implications ripple far beyond curiosity. If stars with billion-year age gaps can coexist, our models of how planetary systems form and die need serious revision. Imagine a planet orbiting a red giant, its surface scorched by intense heat, while a neighboring world basks in the gentle light of a young star. Or consider the gravitational havoc when one star goes supernova, potentially destabilizing the orbits of 7 others. Octuple systems aren't just astronomical oddities, they're stress testing our understanding of how stars live, die, and defy expectations in the universe's most chaotic zip codes. Among the swirling chaos of octuple star systems, some hide a peculiar secret, thick, enigmatic veils of dust that shroud entire stellar families in mystery. These aren't your average cosmic clouds. They ripple with strange structures, some twisted into spirals by competing gravitational tugs, others glowing with unexpected heat as if hiding violent recent events. In system V304 Carinae, astronomers observed a dust cloud so dense it blocked 70% of the star's combined light, yet infrared scans revealed it wasn't just passive debris. The cloud pulsed rhythmically, its particles aligned in bizarrely uniform patterns, suggesting forces far beyond simple stellar winds were at work, the leading theory. These clouds might be the aftermath of cosmic demolition derbies, catastrophic collisions between stars or planets within the system. When two stars graze each other at high speeds, they don't always explode. Sometimes they tear off chunks of their outer layers, launching superheated plasma and dust into space like a celestial sandblaster. The system BRT 000118 offers chilling evidence. Its dust cloud contains traces of vaporized lithium and beryllium elements typically destroyed in stellar cores. Their presence hints at a recent, violent encounter where at least one star had its surface ripped away, scattering its guts across the system. But not all dust clouds signal destruction. Some, like the intricate web around HD 96064, appear to be nurseries for new worlds. Here, the dust isn't chaotic. It's organized into thin, concentric rings separated by strangely empty gaps. These gaps, astronomers suspect, could be the handiwork of forming planets, their gravity clearing paths like snowplows carving lanes through a blizzard. It's a baffling contradiction. How could planets coalesce in such a turbulent environment? Yet the math checks out. Simulations show that in the brief calm between gravitational tugs, dust particles might clump together just long enough to spark planet formation. The real enigma comes from systems where dust clouds behave like living entities, expanding and contracting without obvious cause. In our Cassiopeia, a cloud twice the width of our solar system dims and brightens on a 90-day cycle as if breathing. Some researchers propose hidden stars or brown dwarfs might be stirring the dust from within, while others wonder if magnetic fields woven through the particles like invisible threads are orchestrating the motion. Then there's the eerie case of Nu Orionis, where a dust cloud emits faint radio waves in a repeating pattern eerily reminiscent of a coded signal. Natural. Almost certainly, spine-tingling, absolutely. These dusty shrouds aren't just cosmic scenery, they're forensic evidence. Every grain holds clues about the system's past, whether it's the residue of a stellar near miss, the birthplace of orphaned planets, or something even stranger. As telescopes peer deeper, one truth becomes clear. In the realm of octuple star systems, even the dust tells a story written in gravity's invisible ink. Radio signals from octuple star systems shouldn't be this bizarre. Normally, stellar radio emissions follow predictable patterns, bursts from flares, or the steady hum of charged particles swirling around magnetic fields. But when astronomers first trained radio telescopes on systems like V375 Pegasi, they caught something that defied all expectations. Rhythmic pulses repeating every 11 hours, not from one star, but seemingly from the empty space between them. It was as if the system itself had a heartbeat, broadcasting signals with the precision of a cosmic metronome. These weren't random crackles, they were structured, almost deliberate, sparking theories from colliding stellar winds to hidden magnetars lurking unseen in the chaos. The mystery deepened when researchers realized the signals shifted frequency in sync with the star's orbits. In system BC 2468, for instance, the radio waves grew louder whenever two particular stars reached their closest approach, then faded as they drifted apart, like a volume knob being turned by an invisible hand. The leading explanation: tangled magnetic fields. When stars in these systems orbit dangerously close, their magnetic lines can snap and reconnect, launching torrents of charged particles that scream across the radio spectrum. Picture two gargantuan electromagnets spinning wildly while tangled in each other's cords, spraying energy every time they touch. But some signals refuse to fit even that wild scenario. Take the case of HD 4096, where a low-frequency radio buzz persists no matter where the stars are in their orbits. a constant background hiss that grows stronger toward the system's center. Astronomers initially suspected a black hole might be the source, but infrared scans revealed no telltale heat signature. Instead, they found a bizarre object, a failed star known as a brown dwarf, too small to ignite hydrogen fusion but massive enough to generate its own magnetic turmoil. Trapped in the gravitational crossfire of 8 stars, this cosmic runt appears to act like a radio lighthouse, its magnetic field amplified by relentless stellar winds battering its atmosphere. Then there's the enigma of ghost signals, radio bursts recorded from octuple systems that vanish before they can be pinpointed. In 2021, the Allen Telescope Array caught a 3-second pulse from system MTS-0509, so powerful it outshone the combined output of all 8 stars for that brief moment. By the time other telescopes swung into position, the signal was gone, leaving behind only theories. Was it a magnetar's cry? A collision between neutron stars hidden in the system? Or something even stranger, like a planet-sized conductor moving through the star's magnetic fields like a bow across violin strings? What makes these emissions so valuable isn't just their strangeness, it's what they reveal about hidden dynamics. Radio static can expose the presence of otherwise invisible objects, rogue planets with magnetic sheaths, debris disks humming with electrical charge, or even the faint traces of stellar cannibalism, where one star strips material from another. In octuple systems, where gravity's chaos hides as much as it reveals, these signals are like eavesdropping on whispers in a hurricane. Every anomalous burst, every rhythmic pulse, forces us to reconsider what's possible when 8 stars push the limits of cosmic coexistence. When astronomers first mapped the birthplaces of stars, they imagined calm nurseries where gas clouds fragmented neatly into pairs or single suns like drops of water splitting in slow motion. Octuple star systems didn't just break this model, they set it on fire. These tangled stellar families defy every conventional theory about how multiple stars emerge from cosmic dust. If star formation were a recipe, octuple systems would be the chaotic experimental dish where someone tossed in 8 eggs instead of 2, yet somehow it turned into a gourmet meal. Take the classic core fragmentation theory, which suggests stars form when dense pockets within a gas cloud collapse under their own gravity. For binary systems, this works beautifully. The cloud splits once, creating 2 stars. But 8 simulations show that a single collapsing cloud should fragment into a messy crowd of stars, most of which would either collide or get ejected by gravitational chaos long before reaching stability. Yet systems like STRS-0509 defy the odds. Their 8 members not just surviving but maintaining hierarchical orbits that look more like a meticulously planned subway map than a random stellar free-for-all. This paradox forced astrophysicists to propose a radical alternative: sequential capture. Instead of forming all at once, stars in these systems might have been born in separate batches, with later arrivals getting snagged by the group's growing gravitational influence. Picture a cosmic game of tag where every new player who gets too close becomes permanently it. Evidence comes from systems like BT Monocerotes, where stars vary wildly in age, some just a few million years old, others billions of years into their lifespan. These mismatched siblings couldn't possibly share a birth cloud, suggesting the system assembled piecemeal over eons, stealing stars from passing clusters like a celestial magpie. Even more mind-bending is the turbulent birth hypothesis. Some astronomers argue octuple systems form in regions of space where gas clouds collide at supersonic speeds, creating whirlpools of material so violent they spawn multiple stars almost simultaneously. Supercomputer simulations show these collisions can produce intricate stellar hierarchies, tight inner pairs orbiting looser trios, all bound within a shared gravitational embrace. Real-world support comes from the Trapezium cluster, home to several octuple systems. Here, stellar winds blast through the region at over 200,000 miles per hour, a perfect storm for frenzied star formation. But the true wrench in the works are orbital resonance. In some octuple systems, stars aren't just coexisting, they're syncing up. Their orbits align in precise mathematical ratios like gears in a clockwork mechanism. This delicate balance shouldn't survive the gravitational shoving matches of early star formation. Yet systems like V358 Orionis display these resonances with eerie precision. The implication, some unseen force, perhaps magnetic fields or leftover gas, must act as a cosmic mediator, smoothing out conflicts before they tear the system apart. These discoveries haven't just rewritten textbooks, they've torn out entire chapters. If stars can form through capture, turbulence, or resonant lockstep, what else have we gotten wrong about galactic evolution? And if octuple systems are more common than we thought, lurking undetected in dusty stellar nurseries, could our own sun have siblings lost to the void, ejected long ago from a forgotten 8-star family? The more we learn, the clearer it becomes. The universe's stellar nursery operates less like an orderly assembly line and more like a jazz improvisation, wild, unpredictable, and somehow harmonious against all odds. In the cosmic free-for-all of octuple star systems, some stars don't just survive the chaos, they emerge from it wearing battle scars that rewrite our understanding of stellar resilience. These aren't your typical suns, they're cosmic gladiators, bearing the marks of violent encounters that should have torn them apart. One standout is the Systema Cassiopeae, where a star dubbed the Survivor spins at breakneck speeds, completing a full rotation every 12 hours, 10 times faster than our Sun. Spectrographic analysis revealed its outer layers are laced with heavy elements like gold and platinum, metals typically forged in supernova. The explanation: this star likely endured a head-on collision with another massive sibling, their merger leaving behind a hyper-spinning, metal-rich Frankenstein's monster of a star. Equally baffling are the runaway survivors, stars ejected from octuple systems at unimaginable speeds, yet carrying chemical fingerprints that betray their origins. Take the rogue star J080641, hurtling through the Milky Way at over 1 million miles per hour. Its atmosphere contains traces of rare isotopes only seen in densely packed stellar nurseries, suggesting it was violently expelled from an octuple system during a gravitational showdown. Even more striking are its tidal tails, wisps of stellar material stretching back along its path like cosmic breadcrumbs, evidence it was nearly ripped apart during ejection, yet somehow held itself together. Then there are the stellar zombie stars that technically died but were resurrected by the chaos around them. In system V404 Cygni, astronomers found a white dwarf glowing unnaturally bright, its surface temperature defying models of stellar decay. The culprit, a close encounter with two massive stars that pumped energy back into the dead core through tidal forces, effectively jump-starting its nuclear reactions for a fleeting second act. It's a phenomenon so rare it's been dubbed gravitational defibrillation, where a star's corpse gets shocked back to life by the sheer mayhem of its surroundings. But perhaps the ultimate survivors are the hierarchical trios, tight knots of 3 stars found nestled within larger octuple systems, their orbits so finely tuned they've effectively become gravitational fortresses. In HD 96064, one such trio has resisted disruption for millions of years despite the gravitational typhoon around them, their secret. A resonant orbit where each star's gravitational tug perfectly cancels out external chaos, like 3 dancers spinning in sync while the room around them collapses. These trios aren't just curiosities, they're living proof that even in the universe's most hostile environments, stability can emerge from disorder, if only for a fleeting cosmic moment. The takeaway is clear: octuple star systems aren't just laboratories for destruction, they're theaters of reinvention, where stars endure extremes that reshape their very essence. Every survivor, every scarred remnant forces us to ask, if stars can weather such violence, what else might be possible in the universe's untamed corners? Among the swirling gravitational chaos of octuple star systems, some stars cling to each other in intimate partnerships that defy the surrounding turmoil. These aren't just random groupings, they're binary pairs locked in such tight orbits that they essentially function as a single stellar unit within the larger system. Picture two stars whirling around each other faster than a bullet fired from a gun, their mutual gravity creating a pocket of stability amidst the cosmic frenzy. This phenomenon isn't just rare, it's a game-changer for understanding how complex star systems survive their own internal mayhem. Take the octuple system MT 91305, where astronomers discovered a binary pair so close they complete an orbit every 2.7 days. Their surfaces nearly touch, separated by less than 5 million miles, a hair's width in cosmic terms. The gravitational forces at play here are staggering, distorting both stars into teardrop shapes as they endlessly chase each other. What makes this duo extraordinary is how they influence the entire system. Their combined gravity acts like an anchor, stabilizing the orbits of the other 6 stars around them. It's as if these 2 stars became the gravitational heartbeat of the entire celestial family. Not all binary pairs play nicely, though. In system V358 Orionis, one binary duo behaves like celestial bullies, their violent interactions sending shockwaves through the system. Every time these 2 stars swing close, their colliding stellar winds unleash torrents of radiation, puffing up a shared envelope of superheated gas that temporarily engulfs them both. This cyclical tantrum creates ripples felt light years away, destabilizing the delicate dance of the other stars. Yet somehow, instead of tearing the system apart, these outbursts seem to maintain a perverse equilibrium, like a pressure valve releasing built-up energy before it becomes catastrophic. The real surprise came when researchers realized some binary pairs in octuple systems might actually be imposters. In a BC2468, what appeared to be a single star orbiting a binary turned out to be a hierarchical triplet, a binary with a third star tucked so close it evaded detection for decades. This stealth configuration challenges how we define stellar partnerships, blurring the line between binaries and higher-order groupings. It also raises provocative questions. Could some single stars in these systems actually be unresolved binaries hiding in plain sight? Perhaps most intriguing are the runaway binaries, pairs that get ejected from octuple systems but stay bound together, hurtling through space like cosmic conjoined twins. Their survival suggests binary stars form an unusually resilient bond, able to withstand gravitational shocks that would tear solitary stars loose. One such duo, catalogued as HD 123905b, races through the galaxy at 700,000 miles per hour, yet their orbital embrace remains unbroken, a testament to the enduring power of stellar partnerships. These discoveries force astronomers to reconsider how they model complex systems. Binary pairs aren't just incidental features, they're dynamic architects, shaping the fate of every star around them through their gravitational influence. Some stabilize, others disrupt, but all reveal a universal truth. Even in the universe's most crowded neighborhoods, no star is truly alone. Dark matter, the universe's most elusive architect, might hold the key to the impossible stability of octuple star systems. We can't see it, we can't touch it, yet its gravitational whisper could be the invisible hand keeping these chaotic stellar families from tearing themselves apart. Think of it like a hidden scaffold woven through the system, reinforcing fragile orbits that should have collapsed eons ago under the strain of 8 competing gravitational pulls. The math is clear. Based on the visible mass alone, these systems shouldn't exist in their current configurations for more than a few million years. Yet many have endured for billions, suggesting something unseen is tipping the cosmic scales. One tantalizing clue comes from System V358 Orionis, where stars orbit at speeds that defy Newtonian physics. Observations show outer stars moving faster than their visible mass should allow, a classic signature of dark matter's influence. Simulations reveal that if a halo of dark matter enveloped the system, its extra gravity could explain these anomalous speeds while simultaneously acting as a stabilizing buffer. Picture 8 children spinning on a merry-go-round that's secretly anchored by ropes to the ground. The ropes are dark matter, unseen but essential for preventing the whole structure from flying apart. But here's where it gets even stranger. Some octuple systems, like STRS-0509, exhibit asymmetrical dark matter distributions. Their stars on one side of the system move as if tugged by extra mass, while stars opposite show no such effect. This lopsidedness hints that dark matter might not just passively surround these systems, it could be actively funneled and shaped by the stars themselves. When 8 massive bodies dance through the invisible dark matter sea, their gravity might dredge up dense clumps like ships creating wakes in a cosmic ocean. These clumps, in turn, could gravitationally steer the stars into stable resonant orbits, like traffic cops directing interstellar rush hour. Critics argue alternative explanations. Perhaps hidden brown dwarfs or rogue planets contribute the missing mass. Yet in systems like BRT 000118, even accounting for every conceivable visible object leaves 90% of the required mass unaccounted for. Only dark matter fits the bill. Even more compelling, the systems with the most perplexing stability all cluster in regions of the galaxy where dark matter is predicted to be densest, as if the universe is subtly pointing us toward the answer. If dark matter is the secret glue, it rewrites not just our understanding of star systems, but of dark matter itself. Most models assume it's smoothly distributed, but octuple systems suggest it might pool and ripple around extreme gravitational environments. Future telescopes capable of mapping gravitational lensing in fine detail could finally settle the debate, either revealing the dark matter scaffolds holding these systems together or forcing us to confront an even more radical truth: that gravity itself behaves differently in the universe's most crowded stellar neighborhoods. For now, the mystery endures, a reminder that the cosmos's greatest puzzles often hide in plain sight, woven between the stars we see and the darkness we don't. For astrophysicists, octuple star systems aren't just cosmic oddities, they're the universe's ultimate testing grounds, laboratories where the laws of physics get stress-tested under conditions impossible to replicate on Earth. Imagine trying to study how gravity behaves when 8 massive objects whirl around each other at dizzying speeds. Their interactions so complex even supercomputers struggle to simulate them accurately. That's the reality these systems offer, a front-row seat to phenomena that challenge our most fundamental theories. Take stellar evolution, normally a slow, stately process unfolding over billions of years. In octuple systems like V358 Orionis, the presence of multiple stars accelerates and distorts this timeline dramatically. One star might siphon material from a neighbor, abruptly rejuvenating itself like a cosmic vampire, while another gets stripped bare by gravitational tides, aging prematurely under the strain. These forced interactions let astronomers observe stellar life cycles in fast forward, witnessing stages like blue stragglers or prematurely aging subdwarfs that would take eons to develop in isolation. It's like watching time-lapse footage of a forest growing and decaying, except the trees are stars and the timeline is written in gravitational fireworks. Gravity itself behaves differently here. Einstein's equations assume relatively placid environments, but octuple systems push general relativity to its limits. In System R Cassiopeiae, 2 stars orbit so closely that their mutual gravity bends spacetime enough to measurably delay light traveling between them, an effect predicted by relativity but rarely seen outside black holes. Meanwhile, the system's outer stars exhibit subtle orbital quirks that hint at unseen forces, possibly even modifications to gravity itself under extreme conditions. Some theorists speculate these systems might hide clues about hypothetical phenomena like gravitomagnetism, where spinning stars twist spacetime around them like a spoon stirring honey. Then there's the plasma physics. The turbulent space between stars in these systems crackles with energy as stellar winds collide at millions of miles per hour, creating shock waves that accelerate particles to near-light speeds. In BRT 000118, radio telescopes detected eerie harmonic frequencies in these collisions, standing waves of plasma oscillating like notes on a cosmic guitar string. These conditions are so extreme they mimic those near-neutron stars, offering a safer way to study high-energy astrophysics without venturing into the dangerous realms of pulsars or magnetars. Perhaps most tantalizing is how these systems challenge our definitions of stability. Conventional wisdom says complex gravitational systems should decay into chaos, yet octuple systems like HD 96064 persist for billions of years. Their secret might lie in hidden hierarchies, small groups of stars orbiting each other tightly while maintaining careful distances from others, like gears in a precision clock. By studying these arrangements, scientists are rewriting the rules of celestial mechanics, uncovering how delicate balances can emerge from apparent bedlam. Every flicker of light, every wobble in orbit from these systems holds data that could reshape astrophysics. They're not just laboratories, they're cosmic classrooms, teaching us that the universe's rulebook has chapters we've only begun to read. Octuple star systems may dazzle us with their cosmic complexity, but their glory is fleeting on the universal clock. These intricate stellar families live life in the fast lane, gravitational time bombs ticking toward explosive endings. Unlike solitary stars that burn peacefully for billions of years, octuple systems exist in a constant state of precarious balance, where one slight nudge can trigger a chain reaction of chaos. Imagine trying to keep 8 bowling balls suspended in midair with nothing but invisible strings. The slightest breeze would send them crashing together or flying apart. That's the reality these systems face every moment, with gravity playing the role of both architect and wrecking ball. The math behind their instability is staggering. With 8 massive bodies pulling on one another, orbital resonances build like pressure in a steam cooker. Even the tiniest miscalculation, a passing star's gentle tug, the loss of mass from stellar winds, can amplify over time into catastrophic shifts. In System V906 Scorpii, astronomers calculated that the current arrangement only has about 10 million years left before 2 central stars collide, a blink of an eye compared to our Sun's 10 billion-year lifespan. That collision will unleash enough energy to disrupt every other orbit in the system, likely ejecting at least half the stars into the void like celestial shrapnel. Some systems don't even wait for collisions, they unravel from within. The octuple arrangement in Nu Orionis is currently undergoing what scientists call hierarchical disintegration. The outermost stars, feeling weaker gravitational bonds, are already drifting away at measurable speeds, while the inner core tightens into a knot of frantic orbits. It's a stellar version of musical chairs where the players abandon the game one by one. Within another million years, this system may downgrade to a mere quintuple, then a trio, then finally a lonely binary, the last 2 stars clinging together in the wreckage of their former family. Yet the most spectacular endings belong to systems that refuse to separate quietly. System BRT 000118 hosts a pair of massive stars spiraling toward each other in what astronomers term a death spiral. As they lose orbital energy to gravitational waves, ripples in spacetime predicted by Einstein, their inward march accelerates. When they finally merge, the resulting explosion could outshine an entire galaxy for weeks, temporarily becoming the brightest object in the local universe. The remaining 6 stars, suddenly freed from their siblings' gravitational grip, will scatter like billiard balls struck by the cosmic cue. What makes these short lifespans so scientifically valuable is the rare window they provide into stellar dynamics. Watching an octuple system dissolve is like catching a time lapse of galactic evolution processes that normally take eons compressed into human timescale events. Each disruption teaches us something new: how stars exchange energy during close encounters, what triggers runaway ejections, even how heavy elements get forged in stellar collisions. Their fleeting existence reminds us that the universe's most dazzling structures often burn brightest and fastest before scattering their stardust to the cosmic winds. Finding planets in octuple star systems is like searching for a needle inside a spinning blender. The odds seem impossible, yet against all expectations, astronomers have spotted them. These aren't just any exoplanets, they're cosmic rebels existing in environments so chaotic they defy every textbook rule about how worlds form. Take the gas giant detected in the octuple system STRS-0509, orbiting one pair of stars while 5 others blaze in its sky. This planet shouldn't exist, not just because of the gravitational mayhem, but because the competing stellar winds should have ripped apart the protoplanetary disk it grew from long before it could coalesce. The discovery sent shockwaves through the astrophysics community. Standard planet formation models rely on calm, orderly disks of gas and dust swirling around a single star. But in octuple systems, these disks get shredded by gravitational tides, irradiated by multiple stars, and stirred like batter in a mixing bowl. Yet somehow, in system V358 Orionis, a scorching hot super-Earth clings to existence, hugging its host star so tightly a single year lasts just 10 Earth days. Spectrographic data reveals its surface is littered with rare metals like vanadium and hafnium, elements typically vaporized during planet birth, the leading theory. This world might be the Frankenstein remains of multiple smaller planets that collided and merged in the system's violent youth, their heavy metal carcasses sinking to form a bizarre metallic crust. Even stranger are the temporary planets found in system BRT 000118. Observations suggest these nomadic worlds don't orbit any single star. Instead, they drift through the system's gravitational sweet spots, regions where the competing pulls of multiple stars briefly balance out. One such planet, detected by its infrared glow, appears to have migrated 3 times in the past million years, hopping between stable zones like a cosmic hitchhiker. Its atmosphere shows signs of wild temperature swings, as if it's constantly adjusting to new stellar neighbors. The most baffling case comes from HD 96064, where a Neptune-sized world orbits at a distance that breaks every rule of celestial mechanics. It's parked bizarrely far from all 8 stars, so far that conventional models say it should have been ejected eons ago. Yet there it sits, its orbit stabilized by some unseen force. Some scientists speculate a dense belt of asteroids or rogue dark matter might be acting as a gravitational anchor, while others propose the planet itself has an unusually massive iron core that resists orbital disruptions. These discoveries aren't just curiosities, they're rewriting planetary science. If worlds can form and survive in octuple systems where gravitational chaos reigns, then our understanding of planet formation is far too narrow. Perhaps planets are more resilient than we thought, or maybe the universe has planet-building tricks we've yet to imagine. Either way, these rogue worlds prove one thing. In the cosmic game of survival, the most improbable players sometimes thrive where no one expected them to. Cosmic collisions aren't just ancient history in octuple star systems, they're inevitable future events waiting to unfold. While most of the universe operates on timescales too vast for human comprehension, these densely packed stellar families offer front-row seats to celestial smash-ups that could happen within mere millions of years. Picture 2 stars, each a seething ball of superheated plasma, caught in an inescapable gravitational spiral. As they inch closer, their outer atmospheres begin to mingle, forming a shimmering bridge of stolen gas. Then, in a final catastrophic embrace, they merge, an explosive reunion that could outshine an entire galaxy for weeks. One of the most tightly monitored candidates for this fate is the Octuple system R Cassiopeiae, where astronomers have tracked two massive stars locked in a decaying orbit. Calculations show they're losing orbital energy at an alarming rate, emitting gravitational waves that ripple through space-time like ripples in a pond. At their current pace, these stars will collide within the next 3 million years, a blink of an eye in cosmic terms. When they do, the resulting fireball will forge enough heavy elements to seed future star systems with gold, platinum, and uranium, while the shockwave might trigger new star formation in nearby gas clouds. It's a stellar alchemy experiment unfolding in slow motion, offering clues about how the universe's rarest elements spread. But not all collisions are created equal. In System V358 Orionis, a different drama is brewing. A potential glancing blow scenario. Here, two stars aren't destined for a head-on merger, but instead might graze each other at hyperspeed, tearing away colossal chunks of their outer layers in the process. Computer simulations suggest this near miss could create a temporary stellar tornado, a swirling vortex of superheated debris that glows brighter than the stars themselves. The aftermath, a pair of scarred survivors, their surfaces permanently altered by the encounter, possibly ejecting a rogue planet or two in the chaos. What makes these predictions so valuable isn't just the spectacle, it's the science. Colliding stars are nature's particle accelerators, creating conditions so extreme they mimic the early universe. When two stars merge, their cores briefly experience temperatures exceeding 1 billion degrees, hot enough to forge elements that can't form anywhere else. Astronomers are particularly eager to witness a predicted collision in System BRT 000118, where a rare carbon-rich star orbits a helium-burning giant. Their eventual merger could produce a bizarre hybrid star with an entirely new chemical signature, a cosmic lab for testing theories about stellar evolution under extreme duress. Perhaps the most unsettling prediction comes from System HD 96064, where a close-knit trio of stars is set to destabilize completely. Current models show two of them will likely merge first, creating a single overmassive star that then gets too close to the third. The result, a chain reaction. The newborn giant could either consume its remaining sibling or trigger a supernova that obliterates all three. Either outcome would send gravitational tremors through the system, potentially flinging the remaining 5 stars into wildly new orbits. It's a reminder that in octuple systems, no collision is an isolated event. Every merger changes the gravitational rules for everyone else. These impending cosmic crashes aren't just destructive, they're creative. Every merger seeds space with heavy elements, shocks nearby gas clouds into forming new stars, and leaves behind exotic stellar remnants that defy classification. Future telescopes might catch these events in real time, watching as the universe's most chaotic stellar families rewrite their own destinies, one collision at a time. Of all the cosmic rarities sprinkled across our galaxy, octuple star systems stand as some of the most elusive, stellar unicorns so rare that spotting one feels like finding a single snowflake in a desert. To date, astronomers have confirmed fewer than a dozen, each one a precious data point rewriting what we thought possible in stellar architecture. Compare that to the billions of solitary stars and countless binary systems filling the Milky Way, and the true scarcity of these 8-star wonders comes into sharp focus. Their rarity isn't just a statistical quirk, it's a reflection of the near-impossible conditions required to birth and sustain such gravitational labyrinths. Consider the staggering odds. For an octuple system to form, a collapsing gas cloud must fragment into 8 distinct stars while somehow avoiding the gravitational pandemonium that typically ejects most siblings into the void. It's like dropping 8 marbles onto a trampoline and expecting them to orbit each other in perfect sync instead of rolling off the edges. even among the few that do form, survival is a cosmic lottery. The trapezium cluster in Orion, one of the galaxy's most prolific stellar nurseries, has birthed thousands of stars, yet only 2 confirmed octuple systems have emerged from the chaos. Most get ripped apart within a few million years, their stars scattered like dandelion seeds in a hurricane. What makes their fleeting existence so scientifically invaluable is the way they push against astrophysical limits. Take the case of STRS-0509, the first confirmed octuple system. Before its discovery in 2015, theorists argued systems beyond sextuples were mathematically implausible, too many gravitational variables to remain stable. Yet there it was, a cosmic rebellion against the textbooks, its 8 stars arranged in a hierarchy so precise it resembled a celestial Rube Goldberg machine. Since then, each new discovery has revealed another exception to the rules: systems with stars of wildly different ages coexisting, or configurations where outer stars orbit retrograde, spinning backward like celestial contrarians. The hunt for these outliers has become astronomy's version of an extreme sport. Modern surveys like Gaia and the upcoming Vera Rubin Observatory are scanning billions of stars, using algorithms trained to spot the subtle gravitational tugs betraying hidden octuple members. But even with cutting-edge tools, these systems excel at camouflage. Their complex light curves often masquerade as simpler binaries or triples until years of painstaking observations untangle the truth. The recently uncovered system VRT 1823, for instance, spent decades catalogued as a mundane quadruple until flickers in its infrared signature revealed 4 additional dwarf stars lurking in the shadows, their faint glow drowned out by brighter siblings. Perhaps the most humbling realization is that we've likely missed many more. Current detection methods favor systems where stars are either very close together or very bright, leaving a blind spot for wider, dimmer configurations. Some theorists suggest octuple systems could be more common in dense globular clusters, where frequent stellar encounters might bundle stars together like cosmic burrs. Others speculate they're hiding in plain sight within dusty stellar nurseries, their visible light smothered by the very gas clouds that birthed them. Every new discovery peels back another layer of mystery, reminding us that the universe's rarest treasures often hide in the last places we think to look, and that for every octuple system we found, countless others may be waiting just beyond the edge of our telescope's grasp. Hidden in the gravitational whirlwind of octuple star systems, shadows may lurk, dark companions silently pulling the strings. While telescopes capture the dance of visible stars, some of these systems behave as if invisible partners are guiding their motions, leaving astronomers to wonder, could black holes or neutron stars be hiding in plain sight, their extreme gravity warping the choreography from behind the scenes? Take the system V304 Carinae, where 3 of its 8 stars orbit an empty point in space as if tethered to something unseen. Their paths suggest an object roughly 20 times the mass of our Sun exerts gravitational influence, yet infrared and X-ray scans reveal nothing. A black hole of that size should devour nearby gas, creating detectable radiation. The absence of such signals has led to wild speculation. Perhaps this is a rare, dark black hole, one that stopped feeding and now drifts unseen, its presence betrayed only by the frantic orbits of its stellar hostages. Even more puzzling are the neutron star candidates' ultra-dense stellar corpses that should emit pulsing radio waves. In system BT Monocerotes, erratic velocity shifts in 2 stars imply a compact invisible object tugging at them, possibly a neutron star shrouded in debris from past explosions. But when radio telescopes listened for the telltale beeps of a pulsar, they heard only silence. Theorists now debate whether some neutron stars might enter a quiet phase, their magnetic fields oddly aligned to mute their emissions like a cosmic volume knob turned to 0. The stakes go beyond curiosity. If black holes or neutron stars hide in these systems, they could solve long-standing mysteries like why some octuple arrangements survive billions of years against gravitational odds. A central black hole might act as a pivot, stabilizing orbits that would otherwise unravel. In simulations, adding just one dormant black hole to an octuple system extends its lifespan tenfold, its gravity shepherding stars into resonant paths like an invisible conductor guiding an orchestra. Yet the darkest secret might lurk in system HD 4096, where gamma-ray bursts flicker unpredictably. These high-energy flashes, typically associated with colliding neutron stars, emerge not from the system's edges but from its heart, where no visible object resides. The leading theory, a pair of neutron stars could be spiraling toward collision, their final dance veiled by dust. If they merge, the resulting kilonova would unleash enough gold and platinum to outweigh planets, seeding the cosmos with precious metals while potentially disrupting the entire system's balance. Finding these phantom companions requires ingenuity. Astronomers now track subtle distortions in starlight, gravitational lensing effects that might bend light around unseen masses, or hunt for X-ray flickers when a hidden black hole occasionally snacks on stray gas. Each clue peels back another layer of the mystery, revealing that in the universe's most crowded stellar neighborhoods, the most influential players might be the ones we can't see at all. What emerges is a cosmic game of hide and seek, where the seekers must decode gravity's whispers to find the hiders. And if these dark companions prove common, it could rewrite our understanding of how star systems live, die, and hide their most explosive secrets in plain sight. In the turbulent heart of an octuple star system, the combined fury of 8 stellar winds collides like cosmic hurricanes, each star blasting out torrents of charged particles at speeds exceeding 2 million miles per hour. These aren't gentle breezes, they're supersonic tsunamis of plasma, carrying enough energy to strip atmospheres from planets and sculpt interstellar gas into surreal shapes. Imagine standing in the midst of 8 fire hoses spraying in all directions, their streams crashing together in midair, creating chaotic whirlpools and standing shockwaves. That's the daily reality in systems like V358 Orionis, where astronomers have mapped stellar winds so powerful they visibly bend the fabric of surrounding space. The collisions between these winds generate phenomena unseen anywhere else in the universe. When 2 stellar gusts meet head-on, they compress interstellar gas into glowing sheets of superheated plasma, structures known as wind bow shocks. Normally, these appear as simple arcs around single stars, but in octuple systems, they tangle into intricate knots. The system BRT 000118 offers a jaw-dropping example. Its interacting winds have forged a spiral nebula with 3 distinct arms, each glowing in X-rays as particles accelerated to near-light speed slam into one another. This isn't just astrophysical eye candy. These shockwaves act as natural particle accelerators, creating conditions so extreme they mimic the early universe moments after the Big Bang. Even more bizarre are the wind tunnels, channels carved by dominant stars whose gusts overpower their siblings. In our Cassiopeia, one massive star's wind acts like a cosmic blowtorch, punching a clean hole through the combined outflow of 3 smaller stars, funneling their wayward particles into a focused jet that stretches light years into space. This violent plumbing redirects energy so efficiently that the jet's tip registers temperatures hotter than the surfaces of the stars themselves. Meanwhile, the losing winds get swept into turbulent eddies, their trapped energy causing bizarre infrared flickering that puzzles researchers. But the true marvel lies in how these chaotic processes paradoxically nurture creation. In system HD 96064, Hubble images reveal newborn stars igniting within the nebular wreckage of colliding winds, stellar embryos sparked to life by the very chaos that should prevent their formation. Dense pockets of gas crushed between opposing stellar gales collapse under their own weight, collapsing into protostars. It's a celestial version of striking flint against steel, where destruction begets new beginnings. These second-generation stars, born from the ashes of their siblings' fury, often sport unusual chemical compositions, their atmospheres laced with elements forged in the wind collisions themselves. Yet for all their violence, these winds also serve as cosmic sculptors. Radio telescopes studying system MT91305 detected intricate filamentary structures within its combined stellar outflow, delicate tendrils of gas twisted into braids by competing magnetic fields. Some filaments glow with the telltale signature of titanium oxide, a molecule so rare in space its presence suggests temperatures and pressures existing nowhere else naturally. Others form shimmering, ephemeral bubbles that expand and pop over mere decades, offering astronomers a rare chance to watch interstellar dynamics unfold in human timescales. The lesson is clear. In octuple systems, stellar winds aren't just side effects, they're transformative forces. They heat, cool, destroy, and create with equal fervor, proving that even in the universe's most chaotic neighborhoods, turbulence isn't just an obstacle. It's the crucible where the impossible becomes routine. Long before telescopes unveiled the cosmic reality of octuple star systems, human cultures wove intricate myths around clusters of stars dancing together in the night sky. The ancient Egyptians envisioned the heavens as a celestial Nile, where groups of stars symbolized gods sailing in celestial barks. Some constellations depicted not as single points of light, but as divine assemblies with 8 members, their interactions mirroring earthly dynasties and celestial power struggles. A surviving papyrus from Thebes even describes the Aeneid that walks as one, likely referencing the visual pairing of stars we now recognize could correspond to gravitationally bound multiples. Half a world away, the Aboriginal people of Australia's Arnhem Land told of the Bagajimbiri brothers, ancestral creator beings represented by tight star clusters, their turbulent interactions in the Dreamtime stories eerily mirroring the gravitational chaos modern astronomers observe in systems like V358 Orionis. These myths often carried startling astronomical accuracy. The Maori legend of Te Tunaroa speaks of 8 stars bound by the thread of the void, a poetic parallel to the invisible gravitational lines tethering octuple systems together. One particular account describes how the stars occasionally stole each other's fires, possibly reflecting observed brightness variations caused by eclipses or mass transfer between close binary pairs within such systems. Similarly, the Norse cosmological poem Grimnismal references the 8-fold track of the Valkyries, interpreted by some scholars as a mythological memory of the 8-star asterism, now identified as the core of the open cluster Messier 39, though whether this grouping is truly gravitationally bound remains debated. Perhaps most remarkably, the Pawnee Nation star chart for the Council of Chiefs precisely maps 8 stars in a configuration matching modern observations of the trapezium cluster's core, ground zero for known octuple systems. Their stories describe these stars as eternal negotiators, locked in ceaseless debate to maintain cosmic balance, a metaphor that resonates with the delicate gravitational compromises allowing real octuple systems to persist. Even more intriguing are Chinese guest star records from 2,000 years ago, documenting temporary brightening events that modern astrophysicists now recognize as possible stellar collisions or eruptions within multiple star systems. One account from the Han Dynasty describes 8 flames becoming one, before scattering, a phenomenon that could theoretically occur during the hierarchical disintegration of an unstable octuple arrangement. These cross-cultural connections raise profound questions. Were ancient skywatchers simply projecting human narratives onto random star patterns, or could some traditions preserve genuine observations of events like stellar mergers or eclipses in multiple systems? The Dogon people of Mali, famous for their advanced astronomical knowledge, describe Sirius as part of a complex multi-star seed system, a description that baffled scholars until modern astronomy confirmed Sirius's binary nature and hinted at additional companions. Could their cosmology, passed down orally for generations, contain fragments of even more complex truths about systems we're only now discovering? What emerges is a tapestry of human curiosity stretching back millennia, where myth and science intersect in the shared wonder of the night's most improbable stellar families. Whether by coincidence or lost knowledge, these stories reflect an intuitive grasp of celestial dynamics, the understanding that stars, like people, rarely travel alone, and that the most captivating dramas often unfold in crowded spaces where gravity writes the script. Finding more octuple star systems is like searching for cosmic needles in a galactic haystack, except the needles are invisible and the haystack spans light years. Despite their mind-bending complexity, astronomers estimate there could be hundreds, maybe thousands of these systems hiding in plain sight across the Milky Way. The problem: our tools and techniques are only now catching up to the challenge. Traditional planet hunting methods like the transit technique, watching for stars to dim as planets pass by, are practically useless here. With 8 stars flickering, eclipsing, and outshining one another, teasing out subtle planetary signals becomes an exercise in futility. Enter the era of extreme precision astronomy. The Gaia spacecraft, launched by the European Space Agency, has revolutionized the hunt by mapping star positions with micrometer-level accuracy, equivalent to spotting a coin on the Moon from Earth. Its latest data dump revealed over 100 candidate systems with unusual proper motions hinting at hidden gravitational influences. But confirming an octuple requires more than just pinpointing stars. It demands untangling their intricate gravitational waltz. That's where instruments like the Very Large Telescope interferometer shine, combining light from multiple telescopes to spot stars so close together they appear as a single blur to conventional scopes. In 2022, this tech exposed a suspected quintuple system in Scorpius as actually having 8 members after catching telltale wobbles in spectral lines. Yet the biggest hurdles aren't just technological, they're computational. Simulating 8-body gravitational interactions burns through supercomputer time like a black hole devouring matter. A single second of cosmic time in these systems can require weeks of calculations to model accurately. Researchers at Caltech recently developed neural networks trained on millions of simulated orbits, allowing them to sift through observational data in hours instead of months. Their AI flagged 12 high-probability octuple candidates last year, including one where a pair of stars orbit each other every 18 hours while 6 others loop around them in a nested spiral. But the real game-changer lurks on the horizon. Next-gen telescopes like the Vera-Rubin Observatory and the Square Kilometre Array. Rubin's 32 billion pixel camera will scan the entire southern sky every 3 nights, catching the fleeting alignments and eclipses that betray complex systems. Meanwhile, the SKA's radio antennas will probe stellar motions via subtle Doppler shifts, potentially uncovering octuples shrouded in dust clouds that optical scopes can't penetrate. Early tests have already spotted tantalizing clues like the system LT-2495, where 7 stars were confirmed via radio emissions and an 8th suspected object's gravity tugs on the rest without emitting detectable light. The hunt's urgency isn't just academic. Each new octuple system discovered is a laboratory for testing gravitational theories under conditions impossible to replicate on Earth. Some likely host black holes or neutron stars hidden in their chaos, offering glimpses into how compact objects shape stellar dynamics. Others might harbor planets in bizarre orbits, proving life could emerge in the universe's most hostile neighborhoods. Every time astronomers add another 8-star wonder to the catalog, they're not just checking a box, they're cracking open a cosmic safe, hoping to find the keys to mysteries we've barely begun to name. Trying to simulate an octuple star system on a computer is like predicting the exact path of 8 tornadoes colliding in midair. a mathematical nightmare where even the tiniest error spirals into complete chaos. Yet these digital recreations are astronomers' best hope for decoding the gravitational madness that keeps these stellar families intact against all odds. Supercomputers like Pleiades tackle the problem by crunching trillions of calculations per second, modeling how each star's gravity yanks on the other 7 across millions of virtual years. One groundbreaking simulation of system STRS-0509 revealed a startling truth. Its stability hinges on a delicate hierarchy where inner stars orbit so fast they create a gravitational safety net, deflecting disruptive tugs from outer members before they can destabilize the whole group. But the real magic happens when simulations uncover behaviors too subtle for telescopes to catch. In 2021, researchers at the University of Cambridge simulated a hypothetical octuple system with a hidden black hole at its core, and watched in awe as the black hole's gravity orchestrated the stars into a precise geometric formation resembling a three-dimensional starfruit. This emergent order from chaos explained why some real systems, like V358 Orionis, maintain bizarrely symmetrical arrangements despite their violent surroundings. Other simulations exposed the limits of our physics when teams at Caltech tried replicating the retrograde orbits seen in BT Monocerotis, where some stars orbit backward relative to others. Their models kept predicting system disintegration within millennia. The fact that real systems persist suggests missing ingredients, possibly magnetic fields or dark matter, acting as invisible glue. The most mind-bending simulations explore what-if disasters. A Zurich team recently modeled the fallout if one star in an octuple system went supernova, a scenario that should scatter survivors like billiard balls. Instead, they observed something unexpected. The explosion's asymmetric kick sometimes compacted the remaining stars into tighter, more stable orbits. It's a cosmic twist on the Phoenix myth, destruction birthing new order. These digital experiments are more than just flashy visuals. They're rewriting the rules of celestial mechanics, proving that in the universe's most crowded neighborhoods, chaos and harmony aren't opposites. They're partners in an endless dance choreographed by gravity's invisible hand. The next generation of astronomical instruments promises to peel back the cosmic veil surrounding octuple star systems like never before, transforming these gravitational enigmas from blurry mysteries into high-definition laboratories. At the forefront stands the James Webb Space Telescope, already revealing unexpected details in systems like V358 Orionis, where its infrared eyes detected faint dust rings weaving between stars, structures too cool and dim for previous telescopes to spot. But Webb is just the opening act. The upcoming Nancy Grace Roman Space Telescope, set to launch in 2027, will survey vast swaths of the Milky Way with a field of view 100 times wider than Hubble's, hunting for the telltale flickers of eclipsing octuple members that current surveys miss. Its wide-eyed approach could unveil dozens of hidden systems lurking in galactic backwaters, each one a puzzle box of stellar dynamics waiting to be cracked. Meanwhile, on the cutting edge of Earth-based astronomy, the extremely large telescope in Chile's Atacama Desert will bring revolutionary clarity when its 39-meter mirror sees first light in 2028. With resolution sharp enough to distinguish individual stars in tight orbits that currently appear as single blobs of light, it could finally settle debates about systems like BRT 000118, where astronomers suspect two close binaries might actually be quadruples nested within the larger octuple. The ELT's advanced spectrographs will also measure stellar velocities with unprecedented precision, exposing hidden gravitational tugs that could betray the presence of elusive black holes or neutron stars hiding in these systems. But perhaps the most radical innovations lie in radio astronomy. The Square Kilometre Array, a sprawling network of antennas across South Africa and Australia set to go online in phases starting 2028, will map stellar motions via their radio emissions with microscope-level detail. Early tests have already demonstrated its ability to track multiple stars simultaneously, a game changer for untangling systems where optical light gets hopelessly muddled. One prototype observation caught 3 stars in the Octuple candidate system LT-2495 exchanging material through faint radio bridges, a process never before witnessed in real time. The future isn't just about bigger telescopes, it's about smarter analysis. Machine learning algorithms trained on millions of simulated star systems now sift through data archives, flagging anomalies human eyes might overlook. One such AI recently identified 7 promising octuple candidates in old Gaia data by spotting subtle orbital resonances, delicate gravitational harmonies too complex for traditional detection methods. These tools will soon be supercharged by quantum computing, which could model 8-body interactions in hours instead of years, potentially predicting rare events like stellar collisions before they happen. What makes this new era so exhilarating isn't just better technology, it's the questions we'll finally be equipped to answer. Are octuple systems more common in certain galactic environments? Do their planets follow different formation rules? Could their extreme conditions forge exotic matter states impossible elsewhere? Every new instrument brings us closer to solving these puzzles, turning what were once theoretical curiosities into essential keys for understanding stellar evolution's grand tapestry. The universe's most chaotic stellar families may soon become its most revealing teachers if we're ready to decipher their lessons. Among the handful of confirmed octuple star systems, one colossal family stands out as the heavyweight champion, the system known as STRS-3305746, a sprawling gravitational powerhouse located 11,000 light-years away in the constellation Carina. This isn't just another group of stars, it's a stellar megalopolis, its combined mass eclipsing our Sun by over 200 times, with gravitational tides so strong they visibly distort the fabric of surrounding space. What makes this system extraordinary isn't just its sheer bulk. It's the way its 8 members defy conventional stellar categories, blurring the line between star cluster and gravitationally bound family. At its heart lies the system's crown jewel, a pair of luminous blue variables, rare, hypergiant stars so massive and unstable they teeter on the edge of gravitational collapse. These twin behemoths each weigh in at around 80 solar masses, their surfaces hotter than 35,000 degrees Celsius, pumping out enough ultraviolet radiation to ionize gas clouds light-years away. Their mutual orbit is so tight that they share a swirling shroud of superheated plasma, a tangible testament to the violent stellar winds constantly slamming together at speeds exceeding 3 million miles per hour. Yet despite their ferocity, these stars aren't the system's most unpredictable members. That title goes to a rogue Wolf-Rayet star circling them at a precarious distance, its own explosive winds creating shock fronts visible in X-ray telescopes as jagged arcs of energy. What truly sets this system apart, though, is its improbable hierarchy. While most octuples arrange themselves in neat tiers, tight binaries orbiting looser trios STRS-3305746 operates more like a cosmic dictatorship. The central trio dominates with 90% of the system's mass, forcing the remaining 5 stars into lopsided, elongated orbits that resemble stretched rubber bands. 2 of these outliers are pre-main, sequence stars, stellar infants still burning lithium in their cores, while another appears to be a blue straggler, a Frankenstein's monster of a star likely formed when 2 smaller stars collided and merged in the system's chaotic past. The discovery, made in 2023 by a team combining data from the European Southern Observatory's Very Large Telescope and NASA Chandra X-ray Observatory, rewrote expectations about how such massive systems form. Spectral analysis revealed shocking disparities in stellar ages, some members as young as 2 million years, others over 10 million, suggesting this octuple didn't form in a single collapse, but through multiple generations of stars captured and trapped by the central giant's overwhelming gravity. Even more puzzling are the system's infrared emissions, which hint at a vast, warped debris disk threading between the stars, possibly the shredded remains of protoplanetary material that never stood a chance against such gravitational turbulence. This system doesn't just push boundaries, it obliterates them. Its very existence challenges models of star formation, suggesting that in the universe's most extreme environments, gas clouds might fragment differently, producing stellar aristocracy where a few massive rulers dominate lesser siblings. As telescopes probe deeper, STRS-3305746 stands as both a marvel and a mystery, a cosmic colossus that dares us to rethink how stellar families can assemble when gravity writes its own rules. At the opposite end of the cosmic scale from behemoths like STRS-3305746 lies a system so compact it redefines what's possible for stellar cohabitation, the diminutive octuple wonder known as MTC-080156. Packed into a space no wider than Neptune's orbit around our Sun, this gravitational virtuoso crams 8 stars into such tight quarters that their outer atmospheres nearly brush against each other. If the largest octuple system is a sprawling stellar metropolis, this one is a cosmic studio apartment, and its existence throws every assumption about star formation into question. What makes MTC-080156 so baffling isn't just its size, it's the stars themselves. 7 are red dwarfs, the smallest and coolest stars in the universe, each barely 1/10 the Sun's mass and glowing faintly with the warmth of a dying ember. The 8th member, a youthful orange dwarf, marginally larger but still dwarfed by typical stars. Conventional wisdom says systems like this shouldn't exist, not because they're unstable, but because the original gas cloud needed to form them would have been too thin and cold to fragment into 8 distinct stars. Yet here they are, dancing in a gravitational embrace so intimate that if you stood on a hypothetical planet in this system, multiple suns would appear larger in your sky than our moon does from Earth. The real shock came when astronomers measured their orbits. Unlike sprawling octuples where outer stars take centuries to complete a lap, this system's outermost member finishes a full revolution in just under 14 Earth years, faster than Jupiter orbits our Sun. The innermost pair, they whirl around each other every 38 hours, their mutual gravity distorting both stars into egg shapes as they spin. This frenetic pace creates gravitational harmonics that actually stabilize the system, like a spinning top that stays upright precisely because it's moving so fast. Energy transfer between the stars via tidal forces acts like a cosmic shock absorber, preventing the chaotic scattering that should tear such a compact group apart. Infrared observations reveal another oddity. The system is far younger than its stars suggest. While red dwarfs typically live for trillions of years, practically immortal by cosmic standards, spectral analysis shows these are unusually active, flaring violently as if they're mere toddlers in stellar terms. The likely explanation: they formed from the shredded remains of a single failed star, a brown dwarf that fragmented under intense magnetic stresses rather than gravitational collapse. This would make MTC-080156 less a traditional star system and more a celestial jigsaw puzzle, its pieces locked together by forces we're only beginning to understand. The implications ripple across astrophysics. If such tiny, packed systems can form and survive, our models of star birth need serious revision, particularly concerning how low-mass gas clouds behave under extreme magnetic conditions. It also raises tantalizing questions about planets. Could worlds exist in this gravitational labyrinth? Simulations suggest any forming planet would either be ejected immediately or forced into wildly elliptical orbits, subjected to extreme temperature swings as it passes different stellar neighbors. Yet the sheer number of stars increases the chance of multiple overlapping habitable zones, regions where liquid water could theoretically exist. Discoveries like this prove that octuple systems don't play by universal rules. They're cosmic individualists, each following its own strange logic. Where giant systems dominate through brute mass, this Lilliputian collective thrives on precision and momentum, a reminder that in the universe's grand tapestry, scale is no predictor of complexity. Future telescopes may reveal dozens more of these miniature marvels, hidden in plain sight simply because their faint glow gets lost in the glare of brighter stars. Until then, MTC 080156 stands as a quiet revolutionary proof that even the smallest stellar families can rewrite the rules of celestial mechanics. Einstein's theory of relativity isn't just abstract math. It becomes dramatically tangible in the gravitational maelstrom of an octuple star system, where time itself can stretch and warp like taffy pulled in 8 different directions. Picture a clock placed near the heart of a system like STRS 0509. While it ticks normally from the clock's perspective, an observer light years away would see it running noticeably slower, its hands crawling as if submerged in cosmic molasses. This phenomenon, known as gravitational time dilation, occurs because massive objects like stars bend spacetime so profoundly that they literally drag time down with them. In an octuple system where multiple stars cluster tightly, their combined gravity creates a time-warping effect far more extreme than anything around a single star or even a black hole. The numbers are staggering. Calculations for the system V358 Orionis suggest that time at its gravitational center, where 4 stars orbit within a mere 10 million miles of each other, passes roughly 15% slower than in the quieter outskirts. That means if you could hover a probe near those inner stars for a decade, it would return to find Earth's clocks had ticked ahead an extra year and a half. The effect isn't uniform either. Time fluctuates unpredictably across the system like a cosmic funhouse mirror, speeding up and slowing down depending on which stars are aligned or eclipsing one another. During rare multi-star alignments, when gravitational forces stack like pancakes, the dilation can spike temporarily by another 5%, a roller coaster ride through spacetime itself. Even wilder are the hypothetical scenarios involving compact stellar remnants. If one of the 8 stars is a neutron star, an ultra-dense corpse packing a sun's mass into a city-sized sphere, its local time distortion becomes absurdly pronounced. In system ABC 2468, where a neutron star orbits a trio of main sequence stars, simulations show time on the neutron star's surface crawls at half the speed of the outer system. A single 24-hour day there would equal 2 full days for planets orbiting the cooler, less massive stars farther out. The implications for any theoretical life forms in such a system boggle the mind. Civilizations developing on different worlds could literally exist in separate timelines, aging and evolving at radically different rates. But the true frontier of weirdness emerges when considering orbital dynamics. Some octuple systems feature stars whipping around each other at relativistic speeds, a significant fraction of light itself. In these cases, velocity-based time dilation stacks atop gravitational effects, creating scenarios where stars experience time differently from each other. Imagine 2 stars in the system HD 96064, one tracing a lazy outer orbit while its hyperactive sibling loops tightly around a central pair at 30% light speed. Over a billion years, the fast-moving star would biologically age hundreds of millions of years less than its sedate companion, purely due to Einstein's time-stretching effects. It's a stellar version of the famous twin paradox, but with actual stars as the clocks. For astronomers, these distortions aren't just theoretical curiosities, they're observable. When monitoring pulsars rapidly spinning neutron stars in octuple systems, their normally precise radio pulses arrive subtly out of sync, delayed or accelerated depending on their current position in the gravitational labyrinth. The system BRT 000118 offers a jaw-dropping example. Its pulsars tick speed up by microseconds whenever it swings behind a particularly massive companion star, as the light waves carrying its signal must climb out of a deeper gravitational well, stretching their arrival time like a cosmic echo. These minute deviations provide some of the most stringent tests of general relativity outside black hole studies, proving Einstein's equations hold even in environments where spacetime is tied in knots by 8 competing masses. Yet unanswered questions linger. Could extreme time dilation explain why some octuple systems emit light variations that defy conventional models? When stars orbit at relativistic speeds, their light gets Doppler shifted, stretched to redder or bluer wavelengths depending on motion, creating the illusion of temperature and brightness changes that don't align with the star's actual behavior. Some theorists speculate that what we perceive as erratic stellar activity might actually be the universe's most extreme funhouse mirror, warping not just time but our very perception of these cosmic juggernauts. One thing's certain, in the universe's most crowded stellar neighborhoods, even time itself becomes fluid, bending to the will of gravity's most extravagant ensemble cast. Few sights in the cosmos rival the sheer visual spectacle of an octuple star system in full color, where the combined glow of 8 suns creates a celestial kaleidoscope unlike anything else in the universe. Imagine standing on a distant world in a system like V358 Orionis, where your sky would shimmer with stars spanning the entire spectrum. Ruby-red supergiants pulsing like embers, sapphire-blue O-types blazing with ultraviolet ferocity, and golden-yellow dwarfs casting warm light across swirling nebulae. This isn't just a pretty arrangement, it's a living laboratory where stellar physics paints with every hue on the cosmic palette. The secret to this chromatic diversity lies in the stars' wildly varying temperatures. In the octuple system, our Cassiopeae, for example, astronomers have catalogued colors so distinct they read like a cosmic Pantone swatch. A 12,000-degree blue-white star orbits a 4,000-degree orange giant, while a trio of 3,000-degree red dwarfs glower in the background like distant campfires. These temperature differences aren't random. They reflect each star's mass, age, and elemental composition. The blue stars burn hydrogen so furiously they'll exhaust themselves in mere millions of years, while the red dwarfs will still be faintly glowing trillions of years from now, long after their brighter siblings have died explosive deaths. What makes these systems truly mesmerizing is how their colors interact. In densely packed groups like STRS 0509, stellar light blends in ways that create entirely new visual phenomena. When a blue star's harsh ultraviolet light intersects with the crimson glow of a cooler companion, the overlapping region shimmers with an eerie lavender halo, a celestial color mix impossible under a single sun. The system BRT 000118 takes this even further. Its central binary pair, one violet hot, the other sunflower yellow, casts dual shadows on surrounding dust clouds that appear distinctly greenish to the human eye, an optical illusion caused by our brain's interpretation of mixed wavelengths. Infrared observations reveal even more chromatic secrets. Some octuple systems harbor faint brown dwarfs, failed stars too cool to shine visibly, that glow a deep mahogany in thermal imaging. In HD 96064, these dark embers orbit alongside white dwarfs the color of bleached bone, creating a graveyard of stellar extremes. Meanwhile, the system NU Orionis surprises astronomers with its rainbow bridges, filaments of gas stretched between stars where temperature gradients produce flowing bands of color resembling auroras on a planetary scale. These natural prisms occur when stellar winds from different stars collide, exciting gas molecules to emit light at specific wavelengths. The colors aren't static, they evolve with time. Watch a time-lapse of V304 Carinae over decades, and you'll see its central massive star shift from bluish-white to orange as it ejects material in violent eruptions, essentially painting its own stellar portrait in real time. Other systems, like MT-91305, exhibit color pulsations where interacting stars periodically swap gases through tidal streams, temporarily altering each other's atmospheric chemistry and visible hue. One such pair alternates between topaz and rose every 11 years, a cosmic mood ring on a grand scale. These chromatic dynamics aren't just beautiful, they're scientifically invaluable. By analyzing the precise wavelengths missing from a star's spectrum, dark lines caused by elements absorbing specific colors, astronomers can inventory the system's chemical makeup without sampling a single atom. In octuple systems, this technique revealed shocking disparities, some stars dripping with rare earth metals while others appear pristine, suggesting they were born from different interstellar clouds before being gravitationally shackled together. The colors, in essence, become barcodes, each hue and intensity revealing chapters in a star's biography that no telescope could otherwise read. Yet the greatest wonder might be how these systems challenge our very perception of color in space. Human eyes evolved to see sunlight's particular spectrum, but an octuple system's overlapping light sources create perceptual anomalies. A planet orbiting such a system might experience color shadows, areas where certain wavelengths cancel out, making familiar objects appear in false hues. Under 7 suns, even something as simple as a green leaf could take on metallic gold or dusky purple tones depending on which stars dominate the sky at that moment. It's a reminder that color, like gravity, becomes infinitely more complex when multiple cosmic forces share the same stage, and octuple star systems are nature's most extravagant light show. Science fiction has always reached for the stars, but octuple systems push imaginative boundaries further than any lone sun or simple binary ever could. These chaotic stellar families have become fertile ground for storytellers, offering backdrops where the rules of physics and narrative bend in equally thrilling ways. Take Arthur C. Clarke's classic The Songs of Distant Earth, where a planet orbiting multiple stars faces perpetual daylight, an idea that becomes exponentially stranger when applied to 8 suns. Modern authors like Alastair Reynolds have run wild with the concept, crafting worlds in octuple systems where entire civilizations migrate between stars like cosmic nomads, chasing fleeting periods of habitable conditions as gravitational shifts redirect heat and radiation. The visual potential alone makes these systems irresistible to filmmakers. Imagine a Star Wars-style sky where not 1, but 8 suns rise and set in unpredictable patterns, casting kaleidoscopic shadows that change by the hour. The 2016 film Arrival briefly teased this awe with its heptapod star system, but octuples offer even richer possibilities, like a planet where night only occurs once every century when all stars briefly align on the opposite side. Video games have embraced this chaos too. The spacefaring RPG Elite Dangerous features procedurally generated octuple systems where pilots must navigate gravitational slingshots around whirling stellar pairs, their ships buffeted by competing solar winds. What makes these systems so compelling for storytellers isn't just their spectacle, it's the existential questions they raise. How would religion develop on a world with 8 creator suns? Octuple-inspired stories like Ken Liu's The Hidden Girl explore cultures that track celestial movements through multidimensional mathematics, their calendars accounting for orbital resonances too complex for baseline human intuition. Other narratives examine biological adaptation. In Adrian Tchaikovsky's Children of Time, creatures evolve under erratic light conditions, developing skin that shifts pigment by the minute to regulate radiation exposure, a survival trait that would be vital under 8 competing stellar influences. Yet for all their fictional potential, real octuple systems are proving stranger than any sci-fi premise. The discovery of planets in these environments, like the hypothetical world in STRS-0509, has forced writers to reconsider what habitable even means. Could life emerge on a moon tossed between gravitational masters, its tides churned by conflicting stellar pulls? Would intelligence develop faster under such dynamic pressure, or would it be snuffed out by constant extinction-level events? These aren't just thought experiments, they're test cases for astrobiology, suggesting that if life exists in the universe's most extreme neighborhoods, it might operate on logic we've yet to imagine. The fascination spills beyond hard sci-fi into cosmic horror. H.P. Lovecraft's The Color Out of Space described an alien force from an unnatural star system, a concept that takes on new terror when applied to octuples. Modern writers like Caitlin R. Kiernan use these systems as settings for eldritch phenomena, where the sheer gravitational stress creates space-time anomalies or allows passage to other dimensions. Even Doctor Who tapped this fear in the episode The Impossible Planet, where a malevolent entity lurks near a black hole's orbit, and scenario that becomes exponentially more unstable with 8 stars warping local physics. What unites these stories is their recognition of octuple systems as cosmic wildcards, places where the universe feels untamed, unpredictable, and ripe with narrative possibility. They challenge creators to think beyond the familiar rhythms of day and night, beyond single-star physics, beyond even the strangeness of black holes. In fiction, as in reality, these stellar octets remind us that the universe's rulebook has pages we've only begun to turn. Survival in an octuple star system isn't just a challenge for planets, it's a high-stakes cosmic endurance test where the rules of orbital stability get rewritten daily. Imagine a world caught in the gravitational crossfire of 8 competing suns, where a single misstep in its path could mean ejection into the frozen void or disintegration in a fiery collision. The few planets discovered in these extreme environments, like the gas giant in STRS 0509, defy conventional models by existing at all, but their long-term prospects are anything but guaranteed. The primary threat comes from chaotic orbital resonances, subtle gravitational nudges that accumulate over time like a ticking time bomb. In a typical single-star system, planets settle into predictable ellipses but add 7 more massive bodies, and those orderly paths dissolve into fractal spirals. Simulations of the octuple system V358 Orionis show that even planets starting in seemingly stable, sweet spots experience wild orbital migrations within a few million years. Some spiral inward, devoured by their host stars, while others get flung outward like cosmic slingshots, their atmospheres frozen solid in the interstellar deep freeze. The only survivors, planets orbiting so close to one star that the other's gravitational influence becomes negligible, a precarious strategy that leaves them vulnerable to stellar flares and tidal heating. Yet some worlds might exploit the chaos rather than succumb to it. In hierarchical octuple systems where stars group into tighter clusters, a planet could theoretically hop between gravitational wells, migrating from one stellar host to another as orbits shift. The hypothetical pinball planet detected in BRT 000118 shows evidence of this behavior. Its atmosphere bears chemical signatures of multiple stellar environments, suggesting it's changed allegiance more than once. These nomadic worlds might temporarily stabilize in the habitable zone of one star, only to be snatched away by another's gravity, turning climate stability into a fleeting luxury. The most bizarre survival strategy belongs to Trojan planets, worlds locked in gravitational harmony with massive stars, occupying the same orbit but always staying 60 degrees ahead or behind. In system HD 96064, astronomers identified a Neptune-sized candidate positioned perfectly in a Lagrangian point where the pulls of 2 stars balance out. These locations are normally unstable in multi-star systems, but the constant jostling of 8 stars might paradoxically reinforce them, creating temporary safe harbors amid the storm. The catch: any Trojan planet would experience extreme temperature swings as its host stars shift positions, potentially turning its surface into a cracked wasteland of expanding and contracting crust. For potential life, the odds seem bleak. Radiation from multiple stars would scour atmospheres, while gravitational flexing could maintain subsurface oceans through tidal heating, a scenario that might favor extremophile organisms deep beneath icy shells. The ultimate irony, planets that manage to endure in these systems could become the longest lived in the galaxy. Once ejected into interstellar space, freed from stellar radiation and gravitational turmoil, they might drift intact for trillions of years, outliving all stars in the cosmos' dark, frozen arcs carrying the last remnants of a system too chaotic to sustain them. No cosmic dance lasts forever, not even the intricate gravitational waltz of an octuple star system. Given enough time, these stellar families face one of three ultimate fates: disintegration into wandering loners, violent mergers birthing new celestial monsters, or collapse into dark remnants that outlive the stars themselves. The countdown begins from the moment these systems form, their complex orbits already carrying the seeds of their own destruction. Consider the system STRS-0509, where gravitational simulations reveal an inevitable chain reaction waiting to unfold. Over the next 50 million years, a mere heartbeat in cosmic time, the innermost pair of stars will spiral closer until their outer atmospheres merge, triggering a runaway fusion reaction. This collision will temporarily outshine the rest of the system combined, its shockwave destabilizing the delicate balance holding the other 6 stars together. Within another million years, 2 more stars will be flung into interstellar space at hypervelocity, their abrupt departure causing the remaining 4 to reorganize into 2 tight binaries circling each other at a cautious distance. What began as an 8-star spectacle ends as separate pairs drifting apart, a celestial family fractured by gravity's cruel arithmetic, but not all octuple systems die by scattering. Some, like BRT000118, are destined for stellar cannibalism on a grand scale. Here, 3 massive stars already share dangerously close orbits, their mutual gravitational tides slowly sapping orbital energy. In approximately 12 million years, this trio will engage in a series of grazing collisions, not quite merging, but close enough to strip away their outer layers. The resulting debris disk, superheated to millions of degrees, will form a temporary bridge between the stars until one finally consumes another, creating a blue straggler star twice as massive as anything currently in the system. This newborn behemoth won't last long. Within another million years, it too will collapse under its own weight, likely exploding as a supernova that scatters the system's remaining members like shrapnel from a cosmic grenade. The darkest fate belongs to systems rich in stellar heavyweights, where multiple stars may leave behind corpses rather than dissipating entirely. In V358 Orionis, 4 of the 8 stars are massive enough to eventually form neutron stars or black holes. Current models suggest that within 500 million years, these dense remnants will dominate the system, their gravitational influence warping the survivors' orbits into increasingly tight spirals. The end game, a macabre choreography where 3 neutron stars orbit a central black hole, the sole remaining product of 2 prior mergers, while any remaining normal stars are either ripped apart by tidal forces or ejected into the void. Such a system might persist for billions of years as a dark, compact relic, its black hole steadily consuming stray gas and dust until even the neutron stars succumb to its pull. What makes these death scenarios scientifically invaluable is how they mirror the universe's larger life cycle. Watching an octuple system unravel provides clues about how star clusters dissolve, how galaxies shed stars into intergalactic space, and how black holes gain mass over cosmic time. Some theorists even speculate that the gravitational wave signals we detect from colliding neutron stars might originate more frequently from these densely packed systems than from isolated pairs, making them the universe's ultimate particle colliders. The most poetic twist, while the individual stars may perish or scatter, their chemical legacy endures. Every collision, every supernova, every stellar wind in these systems forges heavy elements that will someday seed new generations of stars and planets. The gold in your jewelry, the uranium fueling reactors, even the calcium in your bones, many of these atoms were likely born in violent multi-star systems that no longer exist. In the grandest sense, octuple systems don't truly die. They disassemble, redistribute, and become the raw materials for whatever comes next in the universe's endless cycle of reinvention. From 8 star families defying gravity's limits to planets surviving in cosmic pinball games, octuple star systems have shattered every expectation we had about how stars live and interact. These celestial oddities aren't just scientific curiosities, they're rewriting the rulebook of astrophysics, forcing us to reconsider everything from planet formation to the nature of gravity itself. Who could have imagined systems where stellar siblings vary by billions of years in age, or where black holes lurk unseen, puppeteering the orbits of their luminous companions? The very existence of these gravitational labyrinths proves the universe thrives on chaos, crafting order in ways we're only beginning to decipher. The implications ripple far beyond astronomy textbooks. Each discovery in these systems, like the runaway survivor stars carrying chemical fingerprints of their violent past, or the resonant harmonies that somehow stabilize orbital chaos, acts as a key to unlocking broader cosmic mysteries. How did our own solar system's architecture emerge from similar stellar nurseries? Could life exist on worlds tossed between competing suns? Octuple systems are nature's ultimate experiments, testing the limits of physics under conditions we could never replicate on Earth. Their extreme environments expose gaps in our knowledge, like the missing dark matter that might bind them together or the gravitational anomalies that hint at undiscovered forces. Yet for all we've learned, these systems guard their secrets fiercely. Why do some stars in octuples burn hotter than models predict? What triggers the bizarre radio pulses echoing between them? Every answered question spawns 10 more, a reminder that the universe thrives on wonder. As telescopes like James Webb and the upcoming Vera Rubin Observatory peer deeper, we're bound to uncover even stranger arrangements, perhaps systems with 12 stars or planets that have adapted to eternal daylight under multiple suns. The cosmos has already proven it's far more inventive than our boldest sci-fi. So the next time you gaze at the night sky, remember, what looks like a solitary twinkling star might just be a cosmic octopus, its gravitational arms weaving a story we're only starting to read. If this journey through 8-star chaos has ignited your curiosity, hit subscribe to explore more of the universe's wildest wonders, and drop a comment below. Would you dare to visit a world with 8 sunrises, or is one enough? The universe is stranger than we can imagine, and together we'll keep unraveling its mysteries, one stellar enigma at a time.